Today, we're tackling a variation of the classic two-sum problem. Your challenge: find the largest possible sum of two distinct numbers in an array that's still strictly less than a given target value k. Think you can do it efficiently? Given an integer array nums and an integer k, our goal is to return the maximum sum, such that there exist two distinct indices I and j in the array where nums I, nums j equals sum, and sum is less than k. If no such pair exists, we should return -1. The core challenge is finding that largest sum while adhering to the less than k constraint. The most straightforward approach is to iterate through all possible pairs of numbers in the array. We'd use nested loops, the outer loop for the first number and the inner loop for the second, ensuring we don't pick the same index twice. For each pair, we calculate their sum. If this sum is less than k and greater than our current maximum sum, we update our maximum. This works, but it's inefficient. Checking every single pair leads to a time complexity of O(n squared, which quickly becomes too slow for larger inputs. Space complexity is constant, as we only store a few variables. The key insight for an optimal solution lies in sorting the array first. Once sorted, we can use the two pointers technique. Initialize one pointer, left, at the beginning of the array and another, right, at the end. We'll maintain a variable maxSum initialized to -1. Inside a loop that continues as long as left is less than right, we calculate the sum of the numbers at both pointers. If this sum is less than k, it means we've found a candidate. We then update maxSum if our current sum is larger. To potentially find an even larger sum, we increment left, moving towards larger numbers. If the current sum is greater than or equal to k, it means our sum is too large. To decrease the sum, we decrement right, moving towards smaller numbers. This systematic narrowing of the search space is why two pointers is so effective here. Let's trace this with an example. Nums equals 34, 23, 1, 24, 75, 33, 54, 8, and k equals 60. First, we sort the array. 1, 8, 23, 24, 33, 34, 54, 75. Left is at 1, right is at 75. Sum is 1 plus 75 equals 76. This is greater than 60, so we decrement right to 54. Now sum is 1 plus 54 equals 55. This is less than 60 and greater than our initial max sum of -1, so max sum becomes 55. We increment left to 8. Sum is 8 plus 54 equals 62. Too high, decrement right to 34. Sum is 8 plus 34 equals 42. Less than 60 but not greater than 55, so max sum remains 55. Increment left to 23. Sum is 23 plus 34 equals 57. Less than 60, update maxSum to 57. Increment left to 24. Sum is 24 plus 34 equals 58. Less than 60, update maxSum to 58. Increment left to 33. Now left is 33 and right is 34. Sum is 33 plus 34 equals 67. Too high, decrement right to 33. Left is no longer less than right, so the loop terminates. After iterating through all possible pairs with our two pointers, the final maximum sum we found that was less than k is 58. This comes from the pair 24 plus 34, which is indeed the largest sum under 60. You'll spot this two pointers pattern when you need to find pairs or subarrays in a sorted array that satisfy a certain condition, especially involving sums or products. If the problem asks for the minimum or maximum of such a pair, and sorting helps establish an order that allows you to make decisions about moving pointers, it's a strong candidate. Sorting the array takes big O of n log n, linearithmic time. The two pointers traversal then takes linear big O of n time. So the overall time complexity is big O of n log n, linearithmic time. Since we perform in-place sorting and use only a few variables, the space complexity is big O of 1, constant time. Mastering the two pointers pattern on sorted arrays is crucial. Try the next problem involving a similar pattern, and don't forget to like and subscribe for more efficient algorithm breakdowns.